For over 40 years, LNG has been shipped safely and securely to our shores, where it's used in over 64 million American homes and various industries. What I'd like to share with you today are LNG basics, the reasons why we liquefy natural gas, and I also like to demonstrate the safe properties of LNG. LNG is simply natural gas in its liquid form. Natural gas is converted to LNG by simply cooling it down to minus 260 degrees Fahrenheit. This process reduces its volume by over 600 times. That's very similar to reducing the volume of a beach ball down to the volume of a ping pong ball. This allows us to transport LNG efficiently by sea. LNG is a cryogenic liquid. There are hazards of thermal burns. However, it is the warmest of all cryogens. It is also an odorless, colorless, non-toxic, and non-corrosive liquid. It is simply condensed natural gas, not compressed, and will be stored under atmospheric pressure in our tanks. As you can see, this batch is minus 260 degrees Fahrenheit. Once again, LNG is a non-corrosive liquid. As you can see, I can pour some on the table and it simply evaporates. It doesn't eat up the table, it simply dissipates. What you'll also notice is the LNG skittering around. This is called the Leidenfrost effect. This is very similar to adding water to a hot iron skillet. Because the table is so much warmer than the boiling point of LNG, it produces an insulating layer, which actually allows it to not evaporate rapidly. Due to the Leidenfrost effect, because my finger is so much hotter than the boiling point of LNG, it produces an insulating layer, which protects my finger from getting burned. Now I'm going to show you how cold minus 260 degrees Fahrenheit is. As you can see, the flour looks the same, but the cold LNG has caused embrittlement of the flour. As you can see, it breaks very easily. In the history of LNG, there's only been one incident that affected anyone on site. This occurred in 1944 in Cleveland, Ohio. This was the time before we knew the full extent of LNG properties. The problem was the tank they used was not 9% nickel steel. Today, 9% nickel steel is used in everything that touches LNG. This is a regular carbon steel pipe. Normally it's pretty tough stuff. This is what we use to make high-pressure gasoline pipelines all across the United States. Usually, carbon steel is pretty tough stuff. As you can see, I was able to dent it, but I could not break it. But if I subject this pipe to the cold LNG, it will cause embrittlement of the pipe just like it did the rose. As you can see, this is what happened to the tank in 1944. Because of this incident, we now have the regulatory framework and the experience to keep this kind of thing from happening again. What I'd like to demonstrate now are the safe properties of LNG. A common myth or misconception is that LNG is more dangerous than other common fuels such as propane or butane. What I'd like to demonstrate now is flame propagation speed. This is the speed that a flame will travel through a flammable cloud of gas. If you think about what it sounds like when you light your propane gas grill, you get a big poof. That's because the flame propagation speed of propane is over 900 miles an hour. When you light it, you get an overpressure, which is actually a small explosion. With LNG, you get a very slow propagation speed. It's what we call a lazy flame. As you can see, you didn't get that big poof that you associate with a propane gas grill. This is what we call a lazy flame. The flame propagation speed is only 12 to 20 miles an hour. According to FERC, although a large amount of energy is stored in LNG, it cannot be released rapidly enough to cause the overpressures associated with an explosion. LNG cannot explode in an unconfined space. What you'll also notice is that the flame is not traveling all the way down to the source of the fuel. What this demonstrates is that the flame can only burn if there's the right concentration of LNG into air. And that concentration is 5 to 15% natural gas into air. So anything above this flame is entirely too lean or to burn, and anything below this tube here is entirely too rich to burn. Another thing about an LNG flame is that there is no black smoke. That's because this reaction only yields carbon dioxide and water. All the carbons are consumed. As you can see, I can stick this nice clear glass into the flame, and it remains nice and clear. Now this is a regular household candle. It's made of a paraffin wax, which is a derivative of oil byproducts. Now if I stick the same beaker into this flame, in just seconds, you'll see unconsumed carbon build up on the beaker. Another common myth or misconception is that LNG, in the unlikely event, will release a flammable cloud of gas that will travel great distances and burn everything in its path. This is simply not true. What I'm going to demonstrate now is that LNG vapors actually behave more like helium versus propane or butane, which actually sink and settle to the ground. As you can see, this acts just like a helium balloon. What this demonstrates is that in the unlikely event of a release, no matter how severe, the LNG vapors will quickly rise, dissipate, and become too lean to burn. What I'm going to do now is actually make some LNG for you by simply cooling down the natural gas vapors captured into this balloon. As you can see the balloon shrinking, that's the natural gas condensing, cooling down, and once again becoming a liquid. If you look closely, you can see a little bit of liquid on the bottom of this balloon. And now the liquid is expanding and regasifying. That's how simple this process is. There are no chemicals or high pressures associated with regasification or liquefaction. If you think about how other hydrocarbons are produced, this is by far the simplest and most environmentally friendly process out there. Cigarettes. These are usually a big no-no at gas stations. That's because gasoline lights around 700 degrees Fahrenheit. I could light this cigarette and get it somewhere between 700 and 800 degrees Fahrenheit. Propane lights around 870 degrees. Kerosene lights around 500 degrees. But since I know that LNG lights at over 1,000 degrees, I can actually light this cigarette, get it as hot as I possibly can, and actually put it out through the cloud of flammable gas and into the cold LNG. As you can see, this cigarette is nice, hot cherry red. This is the area of the flammable cloud of gas. I just put it out in the cold LNG. I can assure you that's very cold. This high ignition temperature is very important for emergency crews if there ever was a fire. Just putting out a crude fire or a gasoline fire simply isn't good enough. There's usually something just hot enough or embers that will reignite these fires. Due to the cold nature of LNG, it is very difficult to get the surrounding areas above 1,000 degrees once this fire is out. Another myth or misconception of LNG is that in the unlikely event of a spill, there's going to be residue or a slick associated in the marine environment. First of all, an LNG spill cannot hurt the marine environment. For one thing, LNG is a lot lighter than water, so it would just float and remain on top. As you can see, the LNG is not mixing with the water. It's just staying on top there. And once the LNG has evaporated, the only thing that's left was a little ice that formed when the LNG evaporated. There are no slicks or residue associated with an LNG spill. To further prove the point that there's nothing left after the LNG has evaporated, I'm going to enjoy this nice, clean, cold, refreshing glass of water. This is a product that I truly believe in. Compared to other, more dangerous hydrocarbons, I feel this is our best choice for clean, safe, cheap energy.